Okay, this is the first of a few videos on work energy power. This is introduction to work energy power. So I've written some things down here on the screen. I just want to talk about it a little bit. Work energy and power. So just understanding some of these terms here. So we'll start off with work. Work is a task performed. Energy is what is consumed to perform the task, and power is a rate of work over time. So if we start off looking at work. So work, there are three types of work. There's mechanical work, and a mechanical work is a force that acts through a distance and is measured in joules. And the formula for that, on your formula sheet, you'll find all of these formulas in there ready for you to use. Work, we just use small w, small k to define work. Work is measured in joules, and it's equal to the force in newtons times distance in meters. And we'll get into how we calculate force, whether it's force times distance or force times acceleration, etc., or force times gravitational constant, depending on the application. So that's mechanical work. Electrical work is the amount of energy consumed when 1 coulomb of electric charge passes through a potential difference of 1 volt. The formula for electrical work is in joules with voltage times the charge in coulombs. And the reasoning there is if 1 coulomb passes through a potential of 1 volt, then 1 joule of work has been done and 1 joule of electric energy has been consumed. And then the last type of work we're going to deal with is temperature-related work. How much work is being done to raise the temperature of a material, water in our examples. So work in joules is equal to K, which is a proportionality constant, which is equal to 4,185. So work in joules is equal to K times N, which is the mass in kilograms. So how many kilograms of water we happen to have, times the change in temperature in delta T. So the change in temperature is usually drawn like this. So you'll see that on your formula sheet where work is equal to K times N times delta T. I just couldn't get a delta in there on this application. And again, the proportionality constant is 4,185 joules of energy to raise 1 kilo of water 1 degree centigrade. Okay, continuing on, let's take a look at force. So when a force of 1 newton is exerted on a body, when 1 kilogram is accelerated at the rate of 1 meter per second. Our formula for force measured in newtons is mass in the kilograms times the acceleration in meters per second. So that's where we get the formula. Force is mass times acceleration. If the object is being lifted, then we use a different formula that gives consideration to gravity. And that is force in newtons, again, is equal to the mass in kilograms times g. So force is equal to m times g, mass times gravitational constant. That gravitational constant is 9.807. We look at power real quick. Power is the rate of doing work. There are two types of power. So there's mechanical power, and it's measured in horsepower. 1 horsepower equals 746 watts. So we get the formula horsepower equals power in watts divided by 746. And then there's electrical power, 2 different types of electrical power measured in watts. We have power, which is equal to work in joules divided by time in seconds, or the one you're more familiar with is power is equal to volts times amperage. And lastly, for the introduction to work energy power, before we get to our calculations, I just want to talk about Newton's 3 laws of motion. Law number 1 is called the law of inertia, and it maintains that every object in motion will remain in motion until an external force acts upon it. Second law is that force is equal to mass times acceleration. The third law is that for every action, there's an equal and opposite reaction. That's called the conservation of momentum.